at some point last week, I mentioned that you can do proofs by induction on any recursive data type, not just the natural numbers. In this video, I'll show you some examples and I'll talk a bit about what's actually going on. So here's the data type for lists, and I'm going to write the function for concatenating two lists by recursion on the first input. This is a reminder of how it works. We say inductively first input, and then we say from the first input, and then in the first case, the first input is empty, and then concatenating is easy because we just output the second list. And in the second case, we have a head element joined onto a tail list, so we can do a recursive call to tail cons the second list, and then we need to join the head back on. So there's several things that we might want to prove about list concatenation. So for example, we might want to prove that concatenating with the empty list leaves it unchanged. So this is just like adding 0 for natural numbers. So I can say, for example, prove that empty concatenate x's is x's, and this I can do by tested for the same reasons that this worked for addition of natural numbers, namely that when you run this program, it sees that the first input is empty and it runs this case. But for the other way round, we can't do this by tested. We're going to have to use induction on lists. So what I'm going to do is I'm going to write inductively x's. So now we're doing a proof by induction on lists. And then I'm going to say from x's. So there are two cases. So the first case is where the list is empty, and then we have to prove empty concatenate empty is empty. And in the second case, we are given that the list splits into a head element and a tail list, and then we have to prove that the thing that we want to prove holds for head cons tail. Now, in the first case, we can prove this by tested because we can just run this program, which is why ask made it invisible. In the second case, what we can do is we can say tested, and ask will try to simplify the left-hand side. And it will actually, so there's an invisible sub-goal here where we say where prove tail cons empty equals tail, and this is the inductive hypothesis that we're given, so we can just say given. Okay. So let's think a bit about what's actually going on here. We want to prove that this equation is true when x is any list. So now every list is either empty or it's built by joining an element onto the front of a smaller list. And we can make every list by starting from the empty list and joining some elements onto the front one by one. So just like we can do a kind of and so on argument for natural numbers, we can also do the same kind of argument for lists. So first we need to prove a base case, which is that the equation is true for the empty list. And then we need to prove an inductive step, which goes like this. We assume that our equation is true for some list, and then we need to prove that it stays true if we join any element onto the front. And then if we prove these two things, then by a and so on argument, we prove that it's true for every list. Now, there's one way that proofs about lists are similar to proofs about natural numbers, which is that both of them have one base case and one inductive step. So for natural numbers, the base case is the zero constructor and the inductive step is the successor constructor. And for lists, the base case is for the empty constructor and the inductive step is for the cons constructor. But there's actually absolutely nothing special about having one of each. So for example, here's a thing that we had in week 4. This is the expression language for Boolean expressions, and the function that evaluates a Boolean expression to an actual Boolean. So a Boolean expression is either a variable, or it's a constant, or it's not of a Boolean expression, or it's and of a Boolean expression, or it's or of a Boolean expression. Now, for example, we could write a function that reverses any expression just by writing the same expression but kind of back to front by so we can do this by inductively E and then from E. So we can do this by recursively turning the ands and the ors backwards. So the variable case stays the same. The constant case stays the same. The not case, we just recursively turn the thing inside backwards. The and case, we're going to recursively call backwards, but we're also going to swap the order of the arguments. Same for the or case. Constant x not what there's the missing. Okay. Now, for example, so doing this should not change the meaning of the expression, because and or the Boolean functions and or are symmetric in their two inputs. So doing this should not change the Boolean that we get from evaluating it. So we should be able to prove that evaluate backwards E gives you the same thing as evaluating E. So we can do this by induction, by proof by induction on Boolean expressions. So I'm going to say inductively E, and then I'm going to say from E, and this will generate the cases. So in general, when you do this, you will get one case per constructor of your data type. And the ones which are not recursive constructors, so ones which do not refer to the data type you're defining among their parameters, look like base cases. And the ones which do, like these three, look like inductive steps. So what's happened here is that, so in this proof, we're going to have 2 base cases and 3 inductive steps because of the shape of this data type. The two base cases ask has actually dealt with automatically because it can detect that they work by tested. And then our three inductive steps, it has not been able to do automatically. By the way, I sincerely hope that this naming bug will be fixed by next week when you're doing exercises on this. I don't want you to have to deal with this. Okay, so you can see, so in each of these three cases, we are given an inductive hypothesis that the equation we want to prove is true for E1 and E2. And we need to prove that it stays true for all of the expressions that we could build from E1 and E2. So you really need to think about this a bit to get your head around it, that this kind of proof method works, that if you prove that this equation is true for variables and constants, and you prove that if you assume it's true for some expressions, then it's true for the not, and or expressions that you can build from it, then you've proved it for every possible Boolean expression. Okay, so in each of these three cases, I can make a bit of progress by writing tested. So it turns out that we can't actually finish this proof because to finish this proof, we need some bit of syntax that I haven't shown you yet. So I'm actually going to leave this here. And then in the other two videos this week, I'm going to show you more bits of syntax for dealing with proofs.